All right, let's do it.
All right. So, okay, I wanted to give a short introduction to latent semantic analysis and also to include just the general concept of topic vector spaces in the context of natural language processing. I guess this is interesting to me, and I think it could be interesting to others because it's closely related to some of the problems we're facing in terms of how to find most similar documents, for example, to show in the KB document suggester, or in the future, perhaps if we want to do other NLP tasks, latent semantic analysis is a technique that is very helpful. So maybe I'll dive into this. Essentially, latent semantic analysis is a set of algorithms or technique in natural language processing that allows us to quote unquote discover hidden topics inside of documents. So this means that instead of just looking at what words appear in a particular document or in a corpus of documents, we assume that there's some sort of underlying meaning behind them. So this could be topic, this could be, I don't know, genre, etc., that we are trying to surface. And this technique also helps us, extract these dimensions in a numerical way. So going from sort of the human language to the text that we see as a sentence or a paragraph or whole page, let's say, or book, to the domain of numbers, where we can represent this in a sort of numerical vector. So it's called latent because we assume that these topics are hidden and we're trying to surface them. So they're these topics that are beyond just one or two different word frequencies. Yeah, and finally, with LSA, we can put together these semantic or topic vectors instead of simply word count vectors. So perhaps this sounds very generic, so I'm going to show with some examples in a second. And just as a side note, this is generally considered, so this is a text processing technique in NLP, but it's also, generally speaking, an unsupervised machine learning mechanism. So in a kind of very rough nutshell, how this works is that we have some raw data. So these are our sentences or documents, whatever, right? So a Wikipedia article that you copy paste from the internet. And then the latent semantic analysis part is this dotted box in the middle, which consists of two steps. First is that we calculate for every document that we have this document term matrix. And then we perform singular value decomposition or some sort of dimensionality reduction technique, which I'm going to show and explain in a second. And finally, we end up with each sentence, each document that we started with encoded in this vector space there, where every kind of number for every document represents its value against a specific topic. So let's look. Then maybe why should I care? Yeah, so we go from just human language to machine language, but also we also persist some of the nuances of human language, such as meaning, at least to some extent. It helps us deal with synonymy. So for example, you know, this problem of I want to go on holiday, I want to go on vacation. These words are synonyms, but if we are just relying on pure word counts, well, the word holiday is not the same as the word vacation. So how would we ever know that they have the same meaning? So a technique like LSA allows these two meanings to be kind of grouped together, these words. Then we also have other problems in these word count models like polysemy, which is a single word can have multiple meanings. So the word mole, for example, is a small burrowing mammal or a sort of mole you can have on your skin, right? LSA, again, to some degree helps with this problem. And very importantly, as a dimensionality reduction technique, it allows us to go from, very huge sparse matrices that are very difficult to process to a much smaller space. So for example, instead of having for every document, instead of encoding it against every single possible word in the English language, right, we would encode it against 200 images. So that's a that has big benefits for retrieval of documents, yeah, for time, of course, etc. Yeah, and of course, most importantly, we can actually compare documents in terms of their meaning, not just in terms of the word frequency and count. So first, I'll start perhaps by just giving the intuition behind just how we transform sentences into vectors. So just bag of words, or word counts, or TF-IDF vectors. But I won't go too much into this. And then, yeah, we'll look at how this then connects to this LSA technique. So if I'm going too fast, please stop me.
So far, so good.
Okay, so just in definitions, they're in the same, yeah, so we speak the same language. So a document is a collection of words. It can also, I suppose, be an empty document, can have just an empty string. But it could be anything from one word to a whole novel. So this really depends on how we, what we consider as a single document for the problem we try to solve. So typical examples are newspaper articles or tweets or SMS messages. All of these are single documents, or a Wikipedia article, for example, is a single document. In other cases, we can look at one paragraph of a document, of a whole article, for example, as a single document. It really depends on what problem we're trying to solve. And then a collection of these documents is a corpus or a body. So this corpus kind of, really defines what kind of topics we're going to uncover and what kind of topics can be differentiable, right? So we often talk about like some medical corpus, which means all a collection of documents that only relate to medical topics, right? So if you go there and try to find something related to, I don't know, dog training, it's likely that you're not going to find something about that. Or if you're looking at, movie reviews, for example, it's unlikely you're going to find something about cooking. So yeah, what corpus is essentially the data that you start with, and that's of course important to dictate the models or the topics that you're going to discover later. So and a dictionary then is all the possible words or combinations of words that exist in your corpus. So the, banana, dog, etc. But also we can create composite words like, and these are called n-grams, but it doesn't really matter. Combinations of words like Elon Musk, Donald Trump, Britney Spears, etc. All of these can be, composite words. And finally, a topic is a collection of words that happen together. So what turns them into a topic is that they appear together in some documents. So it might not be the same word, but they appear in documents that are kind of similar to each other, and therefore they form a topic. And there's multiple ways to get to these topics, but we'll see that in a second. So the ingredients are, I'll show some very basic examples so we can kind of understand what we're talking about. So a corpus is, again, a collection of documents. So here we have 4 documents: the quick brown fox, the slow brown dog, the quick red dog, the lazy yellow fox. So these are 4 documents, and all together they form our very small corpus. Now, the dictionary, or the set of possible, at least one word words or tokens, is the quick brown, fox, slow, dog, red, lazy, yellow, right? So these are it's the set of unique words that we would like to consider for this corpus that we have. We could add more words to this dictionary, but they don't appear in our corpus, so it's not really that meaningful here. And again, on the left, even though they're very short sentences or actually phrases, they are each of them is considered one document. So now that we have these two ingredients, we can actually create this bag of words, quote unquote, matrix, which means for every document in our corpus, so for every short phrase, we can create a table where we have on the in the rows, we have each document, and in the columns, we have each possible word that we have in our dictionary. So, and then for every word in every document, we can say, how many times does this word appear in this document? So for example, in the first sentence, we see the word brown appears, the word fox, the word quick, the word the. So these four words have a 1, and all the other words have a 0. Each of these words could appear more times. So the counts don't have to be 0 or 1. They could be more than 1, for example. So what does this mean? So now for every single sentence, instead of having just the sentence as a text, we actually have a vector of numbers. So in the bottom left, you can see that now the quick brown fox can actually be encoded as 10, 10, 100, 10. It could be also 2s. It doesn't have to be binary in this case. I think maybe this is an unfortunate example. And if we put all of these documents then together, all of these vectors, we actually have a matrix that represents all of the documents, all of these phrases in this in the space of these words, right? So this is essentially just word counts, right? So we count how many times each word appears for each document.
May I ask a question here?
Yeah, of course.
Is there any like weighting involved as well? So meaning that, for example, the is like not happens a lot more often, or is used a lot more often in sentences. So like in order to identify those, they're not considered as unique as, for example, fox, because fox doesn't happen that often.
Yeah, that's a great question. So in this very basic example, no, we're not doing any kind of this filtering. However, it is generally used, what you say, as a part of pre-processing that is shown to generally improve results of, later on tasks. So here we didn't remove the word the, just for demonstration purposes, but there's two ways you could do that. So one is you could have, for every language you deal with, you can have a set of stop words. So words that are just so frequent that you really generally want to exclude them. So those you could just filter out. Perhaps what I didn't really include is also the process of, so the sentence contains words, but what are words? How do you define what a word is? Like in the English language, for example, you're usually separated by a space. However, there might be an apostrophe or something else. Where how do you define what a word is? So in that, after you split a sentence into these words, you can say which of these words or tokens are actually meaningful to keep. The second technique that deals with that is what I was going to show next, is this TFIDF. So this is the idea that, okay, these words might appear a lot of times, but they're actually junk words because they just appear in all documents, so they really have no explanatory power for anything. So we actually want to not count them as heavily or as importantly as other words that make the document stand out. So for example, if we're talking about Wikipedia articles, yeah, the words, I don't know, the or a contributes nothing to the meaning of an article that's about, I don't know, Harry Potter, for example. So the second technique is this term frequency inverse document frequency. So essentially what this technique does is it says, all right, let's start from here where we just counted all the words, but let's actually transform these numbers based on two factors. So the first one is the term frequency. So that means how frequently a term occurs in a specific document. So this is a positive factor. So for every document, if a word appears often as a proportion over the other words in the document, then it seems that this word is important for this document, right? So it gets scored more highly. So for example, a Wikipedia article about Harry Potter is probably going to have the name Harry Potter a lot of times in there, right? So this term, out of all the words in the document, so you say out of 100 words in the document, 5 of them are Harry Potter or 10 of them. That's a lot. So it gets scored more higher. On the other side, we want to say, okay, is this a word that actually appears, it's very common here, but it's also very common across all documents. So this is the inverse document frequency. So it tries to kind of measure the rarity of a document. So we basically say, so it's a logarithm, blah, 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 but basically it says out of, so this specific word, in how many of the total document does it appear, and penalize the term for that. So if it's the word the, for example, the word the will appear in a lot in the Harry Potter Wikipedia article, but it will also appear pretty much in all other documents in Wikipedia. So therefore, it is not an important term. It gets scored more less favorably. In contrast, the word Harry Potter will not appear in many Wikipedia articles, but it will appear a lot in the Harry Potter Wikipedia article. Therefore, it will get scored more highly. So essentially, the words that are irrelevant will get very low values, which will make them, not count, essentially.
Question on that?
Yeah.
Do you have to train each model from scratch and telling them, okay, these are the words that are generally appearing a lot? Or when you start a model from scratch, does it know that?
Well, essentially, if you use Python, for example, or some of the machine learning libraries, they essentially pre-count the words for you, so they can figure out all of these counts automatically. You don't need to do any of that. However, there is a case of creating custom stop words. So if you know that you have a very, very specific corpus where certain words you really want to disregard, you might create a list of words to disregard.
Okay, but otherwise the libraries understand that.
Yeah, otherwise it kind of figures out based on the frequencies. So this is kind of the formula for TFIDF, and I guess TFIDF is an improvement over simple bag of word vectors because it tries to count the relative importance of specific words for each document. And there's, just as a side note, there's different formulas to calculate this inverse document frequency. There's also a problem with documents that have 0. You don't want a division by 0, etc. So there are some tricks to do that. So just as an example, if you had 4 words like blue, bright, sky, sun, you would end up with, so blue sky and bright sun. So these are 2 sentences, 2 documents. If you just count the words in the top left, you end up with kind of 1s and 0s. But if you transform it into a TF-IDF vectorizer vector space, it would give these kind of numbers. Right? So, all right, this is just a recap to understand like how do we go from sentences or documents to matrices. And kind of circling back to the original chart, this borrowed from Databricks, very nice one. So we go from the raw data representation to this document term matrix, right? So for every document, which is every row in this matrix, we have a column, which is every term or every word that we want to consider. We also end up with this dictionary, right? Where we need to know every column, which word does it correspond to. So we need somewhere to store that the position 0 is the word brown, position 1 is the word dog, etc. And so now this is where LSA kicks in. And we're not going to look at this, but basically LSA is a singular value decomposition applied specifically to the purpose of natural language processing. I didn't know about this, that apparently singular value decomposition is used in a lot of other domains, especially in engineering, for some sort of tension calculations. Also, it's very similar to how images are compressed to JPEG. I didn't know about all of this, but apparently there's a lot of other applications. Now, when singular value decomposition is applied to the context of natural language processing specifically, we call it LSA, latent semantic analysis. So what the gist of this very ugly thing is actually summarized very nicely in these lecture slides. So essentially we start from a matrix that is really large. So every document is mapped to every single possible word in our vocabulary. And this matrix could be massive, but also it would be very sparse, most likely. It's a very empty matrix, especially if we're dealing with word counts. So every document will maybe contain only like 1/100th of all the possible words at maximum. And that means that all of the other positions are zeros or very small numbers close to zero. So we take this very large matrix and we decompose it into 3 smaller matrices by using linear algebra. So we split it into one matrix that tells you all your terms, so your words, how they map to specific topics. Now, these topics are abstract. At this point, we don't define anything. We just say like, we wanted to decompose it into X many dimensions. So we say, okay, so this now maps to this many topics. Then we have a topic importance matrix, which essentially tells us, okay, we came up with these topics, but like, okay, some of them are not actually that important. They seem to, a lot of words cluster to that, but actually they don't really contribute much to the total differentiation of one document to the other. And finally, we have this document topics matrix, which is what we want to end up with. We want to a much smaller matrix, which will map every document to new numbers in this other topic space that we have come up with. And yeah, as an example here, I mean, this is done in this Python library in scikit-learn, but essentially we go from this matrix of 1s and 0s on the left side to essentially 2 values, so 2 dimensions, for example, for every sentence. So maybe to say it again, so on the left side in the matrix, we have 9 dimensions, right? So every sentence is mapped against 9 words. And they're 1s and 0s. Again, it could be 1s and 2s and 3s, etc. It's just a coincidence that it's 1s and 0s. On the right side, we have compressed these 1s and 0s into 2 dimensions. But how did we do that exactly? Well, we also generated this other matrix in the process, which tells us every word, how much does it contribute to this topic. So maybe you can think of it as a sort of a linear combination of all of these topics. So the word brown contributes this much to topic 1, the word dog this much, etc. So when each of these words appear in a new document, you can say, okay, take 0.35 plus 0.32 plus 0.35, etc. Add up all these terms and you're going to end up with a new value for the score on topic 1 for this new document.
Tania, could you please go back to the 3, like, yeah, that one. So what you're saying is on the left, we're inputting that. That's like all the things you were explaining before. That's the input. And on the right side, like we do some math and then we get these as a result and then we interpret them after.
Yes, exactly.
Okay, so basically something to do with this operation that we're doing to divide these 3 matrices is creating this concept of a topic.
Exactly.
Okay.
Perhaps a simpler, so there's another technique in LSA where now we're using this singular value decomposition But also we could just be using some simpler, like for example, principal component analysis, which is essentially, let's say, a sentence is in 200 dimensions or something, and actually we want to reduce these 200 dimensions to a smaller number of dimensions. So we do that by creating linear combinations of all the other dimensions, for example. So we say that dimension 1 has this weight, plus dimension 2 has this weight, plus dimension 3 has that weight, etc., etc., etc. And this way we end up with these new dimensions that on one hand they are fewer dimensions, but on the other hand they also contain most of the gist of the original dimension, and therefore if you look at them they also tend to cluster words that are similar in meaning together more often. I don't have a very good example, I think. Well, okay, I have an example for some analysis on some other documents, but for example, if you reduce everything to 2 dimensions, and 2 dimensions is very little, generally speaking, but you would have words that have a similar meaning be very close to each other in these dimensions. Simply because the words that are that have a high weight for that topic appear in these documents. Okay. So yeah, going from here to here, like why is this now interesting? It's essentially interesting because we have gone from just counting words to having a meaning-wise topic vector representation of these new documents in Euclidean space, which means that we can now do operations between documents that have a sense in terms of meaning. So we have vectors, we can add vectors, we can say, I'll have some example from, I can share it later, from subreddits, like you can say the subreddit for Trump minus the subreddit for cats. What subreddit does it lead to? Which is the closest of the difference of the two? You can, of course, as before, as just with word counts, you can look at the distance between these vectors. So that's the cosine similarity, or like the angle between them. And that angle would essentially represent the semantic distance between these two documents. And you can find the closest document in Euclidean distance, so like the absolute distance between 2 points, much faster. So that means you can, because you have much fewer dimensions, you don't have 200,000 dimensions, you have 200 dimensions, you can perform clustering or retrieval of most similar documents much faster than before, without actually losing any of the original meaning. Perhaps an easier analogy to think of is the compression of images, right? Originally they're very high. Well, could be, the original size could be, I don't know, 100 times more, right? You compress it, yet then you look at the image and it looks, you get what the image is, right? You don't lose the meaning of the image because most of the meaning is actually retained through the compression process. So yeah, the good things, I guess, about LSA is that it turns frequencies into actually meaningful topics. And a big plus is that it really reduces dimensionality. Yeah, so it reduces this pretty important problem of sparse matrices and cursive dimensionality when we try to find, for example, the nearest document. But there are some drawbacks, which is that the topics that come out, although are generally, they do make sense if you look at them. However, they're not as perfect as a human would have created them. And there are other techniques, such as more from the statistical world, such as LDIA, so latent Dirichlet allocation, which is generates very humanly interpretable topics. So if the objective is to create humanly interpretable topics, then you need to look at something different. And finally, there's no actually any obvious way to choose the number of dimensions. So that usually has to do more with some other downstream task. So let's say you use this technique to do some other task, for example, I don't know, classification, for example, of texts into spam and not spam. You can use this number of components as a parameter that you tune, and the better your model is. So you choose this number of components or dimensions based on the one that maximizes the performance on the next task. So on the classification, for example. And that's it. Hope it wasn't too complicated.
No. Can you tell us how do we use it at back?
Yeah, so the newest, I guess, implementation that I'm trying to put out now relies on latent semantic analysis, but not using truncated SVG, as we saw before, but using PCA instead. Yeah, so essentially every new knowledge base document that comes in, or maybe I'll start like we have our corpus is all of the possible knowledge base documents that we might suggest to our users. Then we take all of these documents and we call them our corpus, and we construct this topic vector space based on these documents. So essentially we say, let's take all of these documents and decompose them into a set number of dimensions. Now, this is our model that we can store somewhere. And whenever we get new documents, we can score it against the same model. So we say, the word refund appears, the word MacBook appears, etc. So every word has a weight to calculate these new topic vectors. And when a new request, not a request, but a query comes in from a user from Slack, for example, we take that also as a document, a shorter document, but also in similar space. And we also map it to the same topic space. So we say, which words appeared in there? Let's calculate the topic vector values for this specific document. And therefore, we end up with your query as a vector and every knowledge base document as a vector itself. And then we say, which of all of these vectors is it closest in meaning? So that means in our case, we use cosine similarity right now, where that's kind of just the angle, like which knowledge base document has the smallest angle to our query. And in the future, we want to adjust this, not just to use cosine similarity, but also to use other signals, such as have other people find some other similar queries from the past, where similar also in terms of this kind of similarity of this topic vector space. And for that query, find was there any document though that was successfully suggested, so user gave us positive feedback, and if that's the case, then go back and give that document an extra point in our scoring. Therefore, this whole dimensionality reduction for retrieving most similar documents will be also important in the future when we have a lot more documents and a lot more queries.
So just to understand, their similarity is in terms of matching to specific topics, right? It's like
Yes.
How similar are they matching on some specific topic?
Yeah.
Okay. Mm-hmm. Nice. Any other question?
How is this to implement? Like, is it like, it seems like maybe, I don't know, like it seems maybe relatively simple, or how is what is sort of the implementation situation? Is it relatively simple, or is it more complicated, or what do you have to consider when you're implementing this?
I would think it's relatively simple. I think maybe it's a little bit hard right now because we have to go with our existing structure. So kind of, because, you know, we want to keep the old suggester alongside the new suggester. And so I think if we were to write it from scratch, it would be, yeah, much easier. Some questions to answer are, you know, how do you want to store these vector representations, and maybe some smart ways to refresh them. Because if you change your model, then you need to rescore everything against this model. When you use pre-trained embeddings, for example, these embeddings are kind of, you know, stuck in time, right? You know, you can always go back and refer to them, although you could also change the embeddings. But in general, you know, there's these questions of how do you rescore, how do you keep these things in memory and find the similarity, etc.
Interesting.
How often do we retrain now? Do we have to retrain each time we have a new document, for example? Do we retrain only based on the request, or because everything is grouped, it's probably both of them?
Right now, it's not built into retrain automatically. So until we have a sort of more robust pipeline that tells us, oh, this is time to retrain, and these are the criteria in which we will choose to take a new model, the retraining would be done manually. But in theory, it could be done, yeah, when your, in theory, it could be done when your corpus topics change a lot. So it doesn't need to be with every document.
So basically, we would just re-index. If you have a new document, we re-index, but using the existing model, because likely the words inside and the topic didn't shift so much.
Yes, exactly. But if we have a new organization, for example, or a new team that has a lot of documents, it could be the case that they introduce a lot of new topics that we don't know anything about. So we need to let the model know of these topics.
Okay. And so the only way to know that is basically by retraining and looking at the results, if the accuracy or F1 or whatever you use as a metric is better or worse. Or can we predict it before training? My question is, like, can we predict that we need to train before training, or can we only just train and look and say it required training or not and replacing the model?
I don't think it's possible to know that you need to retrain. I mean, you could see whether your topics have shifted, generally speaking. So you could look at some sort of distribution of your documents against this model. So if your new documents are completely outside of, you know, the previous distribution, so you could say, okay, this is time to retrain. But yeah, we don't have that built in right now.
Okay. Another question? Nice. You made your first back talk.
Hannah had a question. She wanted to ask how we rate users' interaction against our score.
How we rate? So
how do we evaluate?
Now, yes.
Yeah, you hear me? Amazing. Yes. Okay, so my question kind of relates to, so if I understood this correctly, we have two ways of adjusting the score for a suggestion, one being the score that we come up with in this matrix, and the other one being the user clicking on whether this was helpful or not, right?
Mm-hmm.
And I wanted to know, like, how are we, yeah, kind of like calculating these two against each other? Like, is the user score more important? Because I mean, also the user could be wrong. Or...
Yeah, that's a great question. So essentially, the all right, how we make suggestions is that, let's say for a user belongs to organization, so they have a set of documents that are eligible to suggest to him, right? This is the set of documents. Each of these documents will get scored. It will get some sort of arbitrary score, right? And then based on the score, all these documents will be ranked, and we show them the top X as long as they're above some sort of threshold. Now the score right now is just this angle, right? So the cosine similarity, but it can be, I think the idea is to make it a linear combination of the cosine similarity plus previous goodness of this document for similar queries. So for example, every positive, I mean, I don't know the exact numbers right now, but the positive, a positive feedback on this document for similar query would be scored, I don't know, 0.2 or something. Negative would be scored 0.5. So it has some sort of weight. We need to decide on this weight. And then of course we want to see, okay, we found this nearest, most similar query, but also, you know, how similar was it really? So this distance of the most similar query is also important. So we would also weight it down or up based on the distance of this query. And yeah, an important question that you ask is like, how do we know that the user feedback is actually any good? Well, the idea is that in the beginning, we would add a pretty conservative weight to this user feedback score, and definitely more positive, like the positive feedback is like a stronger indicator than the negative feedback, because we don't know, you know, just because it was negative, at least in the current setup, doesn't mean that it was not relevant. Right, and then in the future, we could have some, you know, more sophisticated, not just linear combination, but with some sort of, you know, if the value is below that one, then stop considering it, etc. Or if the value is too positive, then it can't be true, stop considering it.
Thanks.
All right, we're on time. So this time we can say goodbye. Thanks a lot, Tania. It was a great, yeah, Adrian says thank you as well from the S-Bahn. It was a great talk. And
Yeah, it was very helpful.
Yeah, very easy to understand, even if difficult. So good job on all that, and looking forward to see the implementation live, actually. Maybe even more exciting.
All right, thank you.
Have a great day, everyone.
Bye-bye.
Ciao.
Thank you. Bye.
Ciao.